Hello everyone, I'm Norman Wahlberger, and thanks for joining me on this adventure where we're going to be looking at polynomial equations. So I'm going to take you through some ideas that we might have a look at. This is a very classical problem. The problem is, how do you solve polynomial equations? Going back, of course, to antiquity, to the Babylonians who were interested in quadratic equations. And then in the 15th, 1600s, a lot of work on the cubic and quartic equations. And then some sort of difficulties as people started to realize that degree 5 and higher equations were somehow different, and then that the standard procedures that the classical mathematicians had developed weren't working that well. So right now, I would say that we're not in a very satisfactory situation, and we're going to look at this problem, and hopefully with some fresh eyes. So let's start by just doing some simple things, which will also allow me to generate a little bit of experience for you working with scientific workplace. Okay, let's say the variable is x, and let's have a very simple equation, say a plus bx equals 0. Okay, there is a polynomial equation of degree 1, admitted very simple. Let's see what our computer tells us is the solution. So we're going to ask it to solve exact, and we're going to solve for x. Okay, we find that x is equal to, right here, x equals minus a over b, provided that b is not equal to 0. Fine. Okay, let's be a little bit more adventurous. Let's look at a quadratic equation, but let's actually do a specific one just to be a little bit more concrete. So let's look at 2 minus 3x plus, say, 5x squared. Okay, there's a quadratic equation. Let us try to solve it. Solve it exact. Okay, we get two solutions, and we see that they're complex here. Why are they complex? There's some i's here. It's because the discriminant of this equation is 3 squared, or minus 3 squared, minus 4 times 2 times 5. So we get complex solutions since the discriminant, which is minus 3 squared minus 4 times a times 5, and that's equal to minus 31. That is negative. Okay, so let's try a variant on that. Let's make the discriminant positive. So we could do that, say, for example, by bumping this 3 up. Let's make it, say, I don't know, 9. And then what will happen is solve exact. Okay, now we're getting solutions in the standard form involving some surds or some square roots. So this involves surds, which for us are not exact numbers. Okay, so we're going to draw upon our wealth of experience here. You all know that I don't believe in square roots, that these are actual numbers. These are algorithms that can be run, but they don't actually finish. So this is a kind of a red herring. And we can see that more clearly and directly by asking for a numerical solution. Solve numeric. Okay, now we get the two solutions, but they're, of course, only approximate. So here are two solutions to 5 decimal places or so. Okay, so we see that even the quadratic equation has complications. We're not really able to solve it in some way. Okay, let's be now more adventurous, and let's go to a cubic equation. Say 3 plus x minus, say, 2x squared. Okay, plus, okay, let's say 4x cubed equals 0. All right, what's going to happen if we try to solve it? Let's first solve it numerically. Okay, so this thing here has 3 solutions, but 2 of them are complex, and 1 of them is real. Okay, and all of them are approximate. So the graph of this thing seems to cross the x-axis in only one point, around x equals minus 0.69. Okay, so, but that's still not really a solution. I mean, those are approximate solutions, but they're not really exact solutions. So let's have a look at trying to solve this thing exactly. Solve exact. Okay, and now we run into some complicated formulas that are really going back to Cardano and Tartaglia and Del Ferro and the Italians, where they realized that the formulas for the cubic equations were rather complicated. They involve cube roots. You can see some cube roots here, and also some square roots inside. And of course, this is very unwieldy. I mean, to actually use this is almost impossible, really, at least before the age of computers. And so this is really a major stumbling block. I mean, people got these cubic equations and they could write down some formulas, but they're really not very useful. So, it's a problem. And if you go to higher degrees, well, let's say you go to 4 degree. Let's see that. Okay, let's modify this a little bit, a 5, and let's stick a quartic term in here. Okay, so now we have a quartic equation, and let's solve it first numerically. We've got 2 real solutions and 2 complex solutions. Okay, now I'm going to just solve it exact. Oh, in this case, this is actually relatively simple. So maybe I've just chosen some really particularly simple ones here. Okay, you see this solution is quite simple. That's not interesting in that it only involves square roots. So that's a happy accident. Let's modify it a little bit. If I change this x to the 4th here to 7x to the 4th, then I don't think that's going to happen again. So now let's calculate the solution of this exactly. Okay, and you can see that it's somewhat analogous to the cubic thing. In fact, the cubic and the quartic equations are closely related. And again, we have some rather complicated formulas involving nested radicals. Okay, so this is somehow the classical story. I mean, it's a very long and laborious story, but the basic idea or direction is the classical idea is to try to reduce such equations to simpler equations involving just radicals. Such as, i.e., x to the n equals a. Okay, so if you have an equation like that, then you express the solution with an nth root, and then you feel confident that you've gotten something, even though we would not accept that as a really legitimate answer. But anyway, that was the orientation of the classical people. And so we want to do something different. Okay, we want to look at this entire story from a new point of view. All right, so let's try to be more algebraic. Okay, so we're going to, we'll dispense with the degree 1 equation, and we're going to go to a degree 2 equation and see if we can kind of think about, how to solve a quadratic equation, maybe in a slightly different way. So let's look at a general equation. So instead of looking at particular numbers, let's look at a general equation. A general quadratic. What does a general quadratic equation look like? Well, it's got a linear term, and I'm going to express that linear term in math mode, c sub 0. Let's say that's the constant term, and then plus, say, c sub 1 times x plus c sub 2 x squared equals 0. Okay, there's our kind of generic quadratic equation where we're not specifying particular values of c0, c1, and c2. Now, note that we really ought to assume that the C2, first of all, even C0, that C0 does not equal 0, because if C0 equals 0, then you can factor out an x, and then it becomes a linear equation. So it's somehow already we've dealt with that. And we can also assume that C2 does not equals 0. Because if C2 equals 0, then we get back to a linear equation. Okay, so we'll make these two assumptions, but otherwise we'll keep the nature of C0, C1, and C2 somewhat open. In particular, we might even eventually think about C0 and C1 and C2 as, variables. Now, you will know, those of you who have watched my videos, that I don't like to think about variables. I rather think about polynumbers, okay? And so we would want to think about those variables as being developed in a polynumber framework. But we're not going to go in that direction. That's an aside that maybe we'll talk about at some other point. In this stage here, we're just going to sort of think about this as a fundamental little equation. Okay, and we want to solve this. Okay, so we want to solve for x. We want to solve for x, well, in terms of C0, C1, and C2. So what kind of thing are we looking for? Well, we're not going to allow radicals. We've just said that because radicals are not something that we can actually calculate. So what are the kinds of things that we can calculate? Right? We're just interested in restricting ourselves to basic algebraic operations, which are addition, subtraction, multiplication, and division. So really what we're doing is at least one approach would be, well, what would happen if you just tried to express x as a polynomial in C0, C1, and C2? Well, it's not too hard to see that that's not going to work. So if x is a polynomial, or let's say a polynumber, if you allow me to do that, in C0, C1, and C2, then this is not going to work. Well, because there's going to be top degrees, and then when you plug in the top degrees, you can see that the top term is not going to be 0. But, and a big but, when polynumbers or polynomials don't work, sometimes polynumbers that keep on going, on-polynumbers, polynomials that keep on going, formal power series, they sometimes have a better chance of working. Okay, and that's an important kind of understanding, that if you can't make polynomials fit what you're doing, you should maybe think in terms of power series, even though maybe what exactly a power series is problematic. But we're just playing around, so let's see what we can do. But how about a on-polynumber, or maybe usually called a power series? Okay, so let's try a power series. And so for that we need a kind of a variable, and we're maybe going to choose one of these things to be a variable. And why don't we try C0? Let's set C0 equal to, say, t, and think of this as a variable for a power series. And we look for a solution which is a on-polynumber or a power series in t. So we look for a solution of the form x equals, maybe a sub 0 plus a sub 1 times t plus a sub 2 times t squared plus 3 dots, carrying on in some fashion or another. Okay, so that's interesting. So what would happen if we just sort of did that? If we sort of tried to fit a polynumber or on-polynumber solution to our original equation? Well, one way of trying to make sense of this, so one way of giving meaning to this is to restrict oneself to just terms of a certain fixed degree or less. That is, we ignore all terms beyond some point. So for example, let's say let's say, to be specific, that we'll let x be we'll go a little bit more than quadratic, maybe a sub 3 t cubed plus a sub 4 t to the fourth plus a sub 5 t to the fifth. And we're going to go only up to 5 or degree 5. Let's say up to degree 5. X is equal to a0 plus a1t plus a2t squared plus a3t cubed plus a4t to the fourth plus a5t to the fifth. So in other words, i.e., what we're doing is we're kind of set t to the 6 equals 0. Okay, that's sort of what we're thinking about. We're trying to just approximately get a hold of something, and so we're just going to agree to truncate our algebra and work in this fixed domain up to, say, degree 6, just to see what happens. All right, so let's plug in and see what we get. We get, okay, so our original expression was c0 plus c1x plus c2x squared. And we've already agreed that c0 is going to be replaced with a slightly easier to deal with t. Okay, and so now we're going to, so let me put that t at the beginning there. We're going to replace the x with the expression that we have for it. So c sub 1 times x. What is x? X is this combination of powers of t. And similarly, this x is also going to be replaced with that particular combination. So now the whole thing is a polynomial in t of degree 10. Let's expand it out to see what it looks like. And let's actually, to make it a little bit easier to understand, we're going to collect terms, so organize it in terms of t. All right, there it is in decreasing powers of t, t to the 10, t to the 9, etc., down to this thing here. So let's have a look at all of this. I want to use the fact that we are agreeing that t to the 6 is 0. So all of these terms from t to the 10 down to the t to the 6 can be removed. All right. So all of this is our original polynomial, and the whole point is to try to set this equal to 0 and solve for x. In this case, it means we have to solve for the a's. Now, this constant term, the constant term gives us, what's the constant term? The constant term is this thing right here. So if we factor this, that's supposed to be equal to 0. So we get two solutions. There are two possibilities. So two possibilities. We could get a sub 0 equals 0. And the other one is that a sub 0 equals, I guess that's just a linear equation. So that's minus c sub 1 divided by c sub 2. And recall that we've agreed that c sub 2 is not 0, so that quotient does make sense. So these two possibilities now sort of provide a fork in the road. There's going to be two kinds of solutions that we're going to be able to generate, one from each one of them. So let's look at the simpler one first. Okay, so we'll start with a sub 0 equals 0. And that's sort of a case, so I'm going to actually make a little subsection here, okay? Okay, what happens if a sub 0 equals 0? Well, that's just one of the terms, so that constant term will be 0. But we want this entire polynomial in t to be 0. So we also get a number of conditions. Maybe I'll start with that one. So a sub 0 equals 0. So we're agreeing on that. And then the linear term here, that's going to be 0. The quadratic term, that's got to be 0. The cubic term, that's going to be 0. Quartic term, that's going to be 0. And the degree 5 coefficient. All right, let's stare at this for a little while. So what are we trying to do? We're trying to solve for the a's in terms of the c's. Okay, we've got a0 here. The second equation is a linear equation in a1. A linear equation in a1 involving a0. Okay, but a0 we've said is 0. So actually this term here is going to be 0. So let's simplify things. All right, I'm going to take that term and I'm going to kill it because of our assumption that a0 is 0. Similarly, this thing here will disappear. Anything else with a0 in it, that will disappear. A0. So we also get these relations. Okay, now we want to solve for a1, a2, a3, a4, and a5. Now, Scientific Workplace actually is able, in some cases, to solve a whole bunch of systems like this. So we're going to solve for a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. Maybe we'll put in a sub 0 just to be complete, even though we already know what that one is. Okay, let's see if Scientific Workplace will figure out what the values are. Hey, it does. So we get these values for our solution. So what is this? A0 is 0, i.e., so now we can write down what x is. X is going to be, actually, but the way I'm going to do this, just to show you something else, I'm going to use a definition. So I'm going to select this, and I'm going to make this definition up here. Okay, that's a new definition. And here are all the definitions. There's only one definition, which is that a1 equals minus 1 over c1. And then here, I'm going to select this and make that into a definition. Make that into a definition. A4 into a definition. And a5 in definition. And I'll just check my definition. So I've got one for each one of these things, a1 through a5. And so now I can go back up to x, which is this thing here. And I can just evaluate this thing. Okay, that's kind of cool. And a0, I should have also selected that as something else. So I'll add that to the list. Okay, 0's on the bottom there. So that'll then kill this thing. And we'll get this as an expression for x. Sorry, try that again. Display this. All right, what have we got here? It looks like we've got something that looks like a solution to our original quadratic expression or quadratic formula as a polynomial or polynumber, an ongoing polynumber in t, and remember t was equal to c0, where I remind you t equals c0. And There's notably there's powers of C1 in the denominators. There are powers of C1 in the denominators, increasing powers. So that means we better ensure, so C1 had better not equal 0. We better remind ourselves, right? We can't allow multiplication or division by 0. And otherwise there are some coefficients. With additional coefficients, what are these coefficients? 1, we'll ignore the minus sign, 2, 5, 14. Now, these are very famous numbers. These are very famous numbers. They are the first 5 Catalan numbers. So it looks like this elementary kind of manipulation has allowed us to find a little formula, at least the start of a formula, for a solution to a quadratic equation in which the Catalan numbers kind of miraculously appear. And then there's then going to be a corresponding other solution, which this the A0 will have to be replaced with this more complicated minus C1 over C2. Okay, but I think we can already see here that we're kind of interested. We're getting somewhere here, right? We're making some progress. We're seeing the Catalan numbers fall out. It means that we're actually touching base with the classical formulas, because it turns out that the Catalan numbers are very closely connected with the square root function, like square root of 1 plus 4x or something or 1 over that has a power series involving Catalan numbers. So it looks like this is maybe some kind of algebraic way of trying to get at the usual square roots. So I think this is a good place to stop. We've made an initial foray into this, and obviously we're raring to go to see how we can go further in this direction. So we'll be doing that next time. Hope you'll join me for that. I'm Noah Wahlberger. Thanks for listening.